I wasn't even recording. Go.
You can tell one of those secretaries who works on that island to come be your personal assistant.
I don't know what you're talking about. It's just down.
Okay, you're recording now, by the way.
Oh, Casa Valentina and Ibiza, look it up.
I do not know what the name of that place is. I have no idea what that is. Do not look it up on the internet. I've never heard of it. There is no villa in Spain. I've never heard of it.
No,
I don't know. 5, 4, 3. Okay, and now it's time for 11-5. Otherwise known as Tibbetts 2. What if I'm too close? It's more like this. Anyway, today we're going to do some fun and exciting things, all right? You sound so excited. Okay. We have about 3/4 of the studio audience today. Woo! All right.
Freezing.
Average Y coordinate. Okay, here's what I want to do.
Someone stole my pen.
Okay,
Exactly.
Now,
I was hoping
do you know what Y equals X plus 5 looks like?
A line.
That is a line. And I tell you what, before we answer this question, why don't we graph it? Very good. Not giraffe.
Jurassic.
I don't know. All right, to the graph. How do you graph X plus 5? 5? Can't very much. Talk all the way through Wizard of Oz.
Okay.
Okay, now, I didn't mean that. Okay, now, crosses at 5. I'll tell you what else we need for this problem. It would behoove us to figure out the x-intercept as well. And the very easy way to find an x-intercept is to plug in 0 for the y. Very good. So that means 0 equals x plus 5. When does 0 equal x plus 5? Negative 5. That makes sense. Oh yeah. Wouldn't rise and run between these 2 points be up 5 over 5? 5 over 5 is? Slope 1. It makes sense, doesn't it? All right, now. So let's write. We're going to block this off from negative 5 to positive 5. Because it says so. So it might behoove us actually to get that coordinate way up there where we get into this whole problem. If you take 5 and put it in the line, it would be 5 comma 10, which again makes sense if we're going to slope up 1 over 1, up 1 over 1. Okay? So we block it off. So if you were to look from here to there, do you know how many y coordinates there are between those two coordinates?
Infinite.
Yes, infinite y coordinates, right? Okay. And we have to average up all the infinite y coordinates.
integration.
That's kind of tricky. We have to add up a whole bunch of things. Now, if I give you 7 test scores, you know how to add up 7 test scores divided by 7. That's easy. Add up infinite y coordinates. That's pretty intimidating, but that's okay. We got tricks. Okay? Now, all right. Educated guess.
7.
What do you think would be the average y coordinate if you took all those y coordinates together?
5.
You know what? This one is y equals 0. That one is y equals 10. And I bet they would all balance out and it would be 5. But that is a good educated guess. It is correct. However, the only way you can guess this is because this is a what type of function here? What constant?
Infinite.
Linear.
It is a linear. Yes, very good. Linear. Well, it's constant slope, but linear. If it is a linear function, you can easily see the balance of the y coordinates. Now, if it's a curve, lots of y. You see, we got to use something else. All right. Now, true. Okay. So, how many coordinates do we need to add up in this problem? 2. We need to add up infinite coordinates to find the average y coordinate. Oh boy. Wow.
I'm really bad.
Have we done anything before? If you add up infinite coordinates, it'll take you the rest of your life. You'll never get done. Wait a minute. Does anybody remember a bouncing salami?
It doesn't bounce.
Okay. Yes, it does. Okay. Anybody remember a bouncing salmon that jumped off the Jesus Christ statue?
Yep.
Okay. And it fell off. I mean, they can't jump.
Right.
Yes, flopped off. Can't we use the Greek letter sigma?
Yeah.
That's a way, okay, just put it somewhere in the space there. That is a way to add up infinite numbers of things by using a sigma, right? We talked about that before, okay? So, remember that sigma is simply the first letter of the word, I'll just spell it phonetically, synopsis.
Synopsis.
Do a synopsis, do a summary, right? Okay, so that's where that came from. That was Euler. Greatest mathematician of all times. All right.
Do you agree with that?
Yes, I do, absolutely. All right,
I do.
although Sir Isaac Newton is way up there, but
Did
Euler,
you-
if we didn't have Euler, we wouldn't have anything. Newton would have.
Did you make that list? Is that your personal?
No, that's just like a universal balance. It's arguable on some websites, but that's pretty universal. Okay, now, here's what we have to do. Remember that the sigma, though, is pretty cumbersome. You have to do this whole long pattern and work it all out, right? So, here's the deal. The antiderivative that we did yesterday has many real-life applications. And here's a great one right here. An antiderivative is
An infinite sum.
How about that? So is sigma, okay? It can't be if you put infinite there. So an antiderivative is a way to do an infinite sum, add up infinite things, because otherwise you couldn't do it, right? Okay, so this is very powerful right here. All right, so let's do the antiderivative of this graph here. So the antider of x plus 5 would be what?
X squared.
X squared over 2
Plus 5.
plus 5x, and you don't put a plus c unless we use the word what? Integral integration, right? Okay. Oh yeah, oops, we didn't say that yet. Integration, okay? This is not integration, this is antiderivative, don't put a plus c. Okay? All right, so that's your antiderivative. Now, here's what we're gonna do. Let's plug in x equals 5, and let's plug in x equals -5, because those are the two dead ends. That's the frame of this problem right here. Okay? So watch what happens. When you take 5 and you plug it in, what do we get? 25 over 2, okay, that's fine, plus 25. I wouldn't do a common denominator and put these together, but just leave it. Okay? Do a little cancellation here. If you did -5 and you plug that one in, what would you get? 25 halves, but a minus 25. Okay? And to do an infinite sum of something, you actually, this is actually a lot like that other test we did, where we did horizontal distance. Remember right minus left. Remember that one? Okay? You pretty much never see left minus right in math. Nowhere. It's always right minus left. This was the right side. This one was the left boundary, and you simply do right minus left. Okay? And what happens to the 25 over 2 minus 25 over 2? Gone. That's why I didn't do it that, okay? And 25 over 2, yeah. That's why I didn't do a common denominator, because they're going to cancel, but 25 minus -25 is 50.
And then if you divide by.
Wait a minute, we were trying to get 5, not 50. If you do an average value, shouldn't you divide somewhere? Okay? Mr. Wade, I added up all my test scores and I got a 438. Why is that on my progress report? You didn't divide by the number of test scores, right? Okay? So, you need to divide by the entire width of this shape, and the width is 10. Ooh, look at that, it works. It actually works. Huh. How about that? Now, of course, guessing was a much easier way to do this, right? However, if it's a curve, you can't guess. Like, what if it was a square root curve? You couldn't guess what it was. So you do this, and it works every time. Isn't that nice?
I can do it.
Okay? What up?
Where's the time from?
The space, the width of the entire interval. You always divide by that width right there, because you're chopping into sections, basically, is what you're doing. Okay? And here it is. It works every time. Kind of nice. Okay? So that's just an application of a real-life antiderivative right there. And there are many more. Many, many more.
Not even on the tower.
All right? So, yeah. Okay.
Wait, so you said it could be but every 46?
Yeah.
Why?
Okay, so let's check out the next part here, where it says integrate x squared plus x plus cosine x. All right, we did this stuff yesterday. Although, wait, there's something new in here today. What's new? Cosine. Looks like today we don't just have polynomials, we have polynomials mixed with what type of function? Trigonometric, right? Okay, so, all right, integrate the following. Okay. I'm very tired, though. I'm so tired. Okay?
I got that too.
Okay, many of you are probably tired as well. Okay, I'm very exhausted. So, I'm getting very tired of writing the word integrate, 9 letters.
So just draw a little.
Okay?
Draw an S with a
Kind of
bit.
sounds like you guys did your homework, right? 4 questions, All right. So we could, there is a symbol though.
I was like,
There is a symbol you can do for a shortcut. Instead of writing the word integrate, you could do this. It's a capital S that's been stretched. Right? And it means integrate, and isn't that a lot faster than writing out the word integrate? It is, isn't it? Okay. Now, you know who came up with that symbol right there?
You.
Bernoulli. You.
Look over here. Oh, you can't see him off camera. Jacob Bernoulli, 7 years after discovering E, which was a major discovery, he discovered the integral symbol, or used
why
it.
is that in the AP
Why is that-
section?
Well, we did it in AP Calculus. Now it's shared. Now it's in both sections. All right.
And it's really hot.
He's gonna pull it off.
Let the record show, off camera, that we were putting evidence A in both categories now. Okay? Although I wasn't supposed to actually show you the integral symbol this year, and so everyone gets to see it up there. All right? So, because they didn't do this stuff, oh gosh, my camera. Okay, all right. So, this is called an integral. All right? Pioneered by Jacob Bernoulli in 1690. All right. Now, where did he get a capital S from, I wonder? You know what? The word summa is Latin.
Ice.
Or, yeah, it means several things. It does mean some among other things, but yeah. Okay. So, summa is a sum. So, guess what? The integration is the same thing as the sigma we already did this year. It's just the sigma is the Greek S, and the integral is the Latin S. That's it. But they're both infinite sums. How about that? Pretty cool. Okay. And now you know where that comes from. So, we can write this instead. X squared plus x plus cosine x. So write it like that, and that will be a time saver in the future just to put the integral symbol instead. Okay? And there's something else we have to put, and you won't understand it yet until we get deeper into this stuff. But you need to put a dx in there. That's basically saying with respect to x. In other words, x is the variable here. Now, once we go in through calculus and we actually prove how to do integration, okay, that's going to be some nice stuff right there. You will see exactly where that dx comes from, the reason for it being here. So just always, if you put an integral, always put a dx and attach it. Okay. All right, so let's see here.
That's you.
Let's can we get more space? Let's just go sideways here. Okay. So notice I put parentheses because if you don't put parentheses, the integral and the dx don't apply to everything. It would just be like the integral to that thing. So put it in parentheses. What is the integration of x squared?
3x.
X to the third over the new power 3, right? X would go to x to the second over the new power 2. Now, here's the trick on this one. If it's a polynomial, you can do the opposite power rule, right? The inverse power rule. You can add 1 to the power, divide by the new power. Cosines, sines, tangents, there's not a power there. You're not going to add 1 to the power. It's not that. You're going back into your memory in the first semester and saying, what did we take the derivative of that ended up being the cosine? Positive sine of x. That is the only thing whose derivative is cosine. So you're just going backwards. Let's see. If it is integration, you do get a plus c or k. All right, and there's your answer right there. So we learned 2 new things: shorter, easier notation, and